Welcome to part 6 of the integration topic, where we're going to be looking at exponential functions. In particular, we're looking at e to the x. Remember, e to the x is that special exponential function that when we derive it, we just get e to the x. So any exponential function, when we derive it, we get another exponential function, but this is the special exponential that just gives itself. So therefore, when we go the other way, when we integrate e to the x, we just get itself, right? Along with the constant of integration. So let's write this down properly, and then we'll also look at the chain rule as well. So the integral of e to the x with respect to x is e to the x plus c. What about the chain rule? How do we work out the integral of e to the power of ax plus b? Well, let's first think about what happens when we derive these kind of functions. So just as a little example, if I gave you e to the 3x plus 1, can you remember how to derive this? What we need to do is look at the derivative of the power. So what's the derivative of 3x plus 1? Well, that's just 3. And then we multiply it by the exact same exponential function. So that's how we would derive. Remember, with chain rules, we just seek to compensate if we need to. So in this case, we want to divide through by the a. Right, so there'll be a 1 on a out the front, and then the exact same exponential plus our constant of integration. So just double checking by differentiating our answer here. If we had to differentiate this, the a, which is the derivative of this ax plus b, the a would come out the front. However, it would cancel with this 1 on a, leaving us just with e to the power of ax plus b, which is exactly what we want. So with this basic rule, and also this chain rule, let's do some examples to understand this a little better. Our first example is a definite integral between 0 and 2 of 4 e to the x. Remember, any constants can be brought out the front of the integral sign. So let's just rewrite our integral first. And now we can focus on finding the integral of e to the x. And that is simply e to the x. That's nice. We'll put our 2 and 0 there so that we can apply the fundamental theorem of calculus, which is where we substitute in 2, and then we take away the result and we substitute in 0. Now remember, anything to the power of 0 is just 1. And while we could go and compute this as a decimal number, which is 25.5 approximately, we know this because e has a specific value, 2.718 and so on. But ultimately, this decimal value is unnecessary, and we can just keep our answer in exact form. So 4 outside of e squared minus 1 is our answer for the first example. On to example 2, which is an indefinite integral. So we have the integral of e to the 2x minus e to the power of negative x. So let's do it one bit at a time. Let's focus on the e to the 2x. We need to think about the derivative of 2x which is 2, and so we need to put it over, so 1 over 2. That is so that if we were to differentiate this term, when the 2 comes out the front, it cancels with the half to leave us just with e to the 2x. So there's our first term. What's going to happen here with all the negatives? Well, because a minus 1 over 1 comes out the front, our negatives actually combine to form a positive. And so we have e to the minus x. So just take time to differentiate this and see what would happen. If we differentiated this term here, the minus 1 would come out the front, and that would give us minus e to the minus x. So this is correct. Last thing, because it's an indefinite integral, we add on our constant of integration. And that's example 2. Now, what if we are asked to find the integral of some exponential where it has a different base? Maybe it's 2 to the x, or 3 to the x, or something else that is different to e to the x. What do we do then? Well, just like before we actually state what this integral is, let's think about the derivative of y equals a to the x. How would we calculate this? The first thing for us to do is to attempt to change the base around. Because we know that e to the x is the exponential that we can differentiate, if we can change this base using some log laws, that's the way to go. So let's a little bit of a throwback, but we've got to apply the log laws. Remember, logarithms and exponentials are just opposites of each other. They're inverse functions. So using either the definition or by taking log base a of both sides, we get that log base a of y is just equal to x. Right? The log base a and the base of a in the exponential cancel out to leave us just with the power x. Or you can think about it using your log laws. Then we can do a change of base, and this is where we get to choose the base. So for us, we want log base e or ln. And so our change of base rule states that we can turn this into this. That's still equal to x. Now this ln a, it is just a constant, and we're going to multiply it to the other side. So this constant ln a is multiplied by the x. And now we just want to get, I'll give ourselves a bit more room, we just want to get y by itself. So how are we going to undo this log base e? Well, let's raise both sides of the equation to the power of e. So we'll have e to the power of this. That just cancels to give us y by itself. And on the right hand side we have e to the power of ln a x. Remember, ln a is just a constant. So we've now got our function in the form y equals e to the power of a constant times x, and this is something that we can differentiate. So we can say dy dx is equal to, we bring the constant out the front, and then we have the exact same exponential. However, just to make things look a little bit nicer, notice that this bit here, e to the power of ln a x, this is just y. Right, so this bit here, that's y. But y is a to the x. So let's replace what's in this circle with a to the power of x. And so the derivative dy dx is equal to ln a, just a constant, multiplied by a to the x. So that is a little refresher of the derivative of an exponential that doesn't have base e. So let's use this now to help us come up with the integral. This is just a constant that we need to compensate for. So going back to our proper notes, when we find the integral, we just need to compensate for that constant. 1 over ln a will be out the front, and then we have a to the power of x plus our constant of integration. So if we were to derive this with everything we just saw, and ln a ends up coming out the front, right, just over here. All that ended up happening after all that was that an ln a appeared out the front. We don't want an ln a. There's no ln a here. So we need to compensate by having that on the bottom. Finally, our regular constant of integration. So with that rule now established, let's do one example to see how it works. Let's find the integral of 2 to the power of x. So following the rule, we still have our exponential 2 to the x, but we need to compensate by providing a 1 on ln 2. And that's it. Pretty easy, hey? Okay, that finishes off our lesson on the integration of exponential functions.